the eigenfunction of momentum operator. The momentum operator p hat is defined as minus I times h bar times d dx. The eigenvalue equation is minus I h bar d dx psi of x equal p psi of x. Now x is real and p is also real. We require that p is real, and psi of x is a complex function of x. Since psi is complex function of x, we can write down psi x as in polar coordinate form r of x e to the I theta x. So this is the polar form of complex number. So psi of x equal to r of x times e to the power I times theta of x. Now, when we substitute psi of x into here, we have minus I h bar d dx bracket r of x e I theta of x equal p times r of x e to I theta of x. We can apply the operator derivative on the products of this function. We have minus I h bar d dx r x times, we apply on the first term, then times I theta of x minus I h bar. The first term remains the same, then derivative put on the second term. So d dx e to the I theta of x. On the right side equal p r of x e to the I of theta of x. So on the left side, this term, okay, we write down here minus I h bar d dx r of x times e to the I theta x minus I h bar r of x. So this term, when I make derivative, I have e to the I theta of x and time I d dx theta of x. And on the right side, I have p r of x e I theta of x. Now, we cancel out on the both term, both side, e to the I theta of x. So I have here this one cancelled, this one cancelled, this one. So I have here equal minus I h bar d dx r of x minus I h bar r of x I d dx theta of x equal p r of x. Now, since I times I equal to I squared equal to minus 1, so cancel out with minus sign. So on the left side, I write down here minus I h bar d dx r of x plus h bar r of x d dx theta of x equal to p r of x. I write down, if I move this term on the left, I have here this. I have here h bar r of x d dx theta of x minus p r of x. I just move this term on the left. I change the minus sign. Minus I h bar d dx r of x. This term equal to 0. Now, the first two terms are only real part, and this one's imaginary part. So I have two equations. One equation is this, h bar r of x d dx theta x minus p r x. The first two term equal to 0. This one I call equation 1. The second one, this imaginary term I have here is minus h bar d dx r of x equal 0. this is the second equation. So I have two equations. The first equation, equation 1, the first equation I have here this Rx, I take it out, cancelled. So I have H bar D dx theta of x minus p equal 0. Now, so therefore I write down here, therefore d dx theta of x equal p divided by h bar. Now, therefore, theta d theta of x equal p bar dx. If I integral d theta of x equal p bar dx, so I get theta of x equal p divided by h bar times x plus c. C is a real number, a constant, integral constant. Now, equation 2, I have minus h bar d dx r of x equal 0, or d dx r of x equal 0. Therefore, r of x equal a constant. This constant I write down as c prime. So c prime is a real number, constant. Therefore, my psi of x in the beginning, as I defined in the beginning, equal r of x e to the I theta of x. So this one equal, so r of x c prime e to the I theta. So I times theta equal here p divided by this, p divided by h bar x plus c this. So equal c prime e to the I e to the I c and e to the I p h bar x, and this constant and times another constant e to the ic I define as a new constant. I call c double prime e to I p h bar x, and c double prime is a complex constant. Now, in summary, we have here the momentum operator p hat is defined as minus I h bar d dx. The eigenvalue problem for this operator is p axiom psi of x equal p psi of x. Now, this p is real number and psi of x equal a constant time e to the I p bar x. This is the answer.